So hi, welcome back to the lecture series in abstract major theory with course code MMT E305 and MTH 701. Today in this lecture we will discuss absolutely continuous functions. Abs- absolutely continuous functions. Okay, so let me first define absolutely continuous function. A function from the closed interval AB to R, it's a real valued function on closed and boundary interval AB, is said to be absolutely continuous, is said to be absolutely continuous if for each epsilon positive there exists a delta positive, such that for every finite disjoint collection, such that for every finite disjoint collection, of open intervals, okay, they are all open intervals of such that for every finite disjoint collection AK BK of open intervals in AB, such that for every finite disjoint collection of open intervals in AB, if the sum of these open intervals, sum of the lengths of these open intervals is less than delta, if this summation k runs from 1 to n, if summation k runs from 1 to n, bk minus ak is less than delta, then this sum is actually the variation of the functions over these intervals. It's k runs from 1 to n mod of f of bk minus f of ak is less than epsilon. So we don't need to write mod here because bk is greater than ak, okay. So the function f from closed interval AB to R is said to be absolutely continuous if for each epsilon positive there exists a delta positive, such that for every finite disjoint collection of open intervals AK BK in this interval AB, and whenever the sum of the lengths of these intervals AK BK is less than delta, then this summation k runs from 1 to n mod of f of BK minus f of AK should be less than epsilon. So if we choose, since this is true for every finite disjoint collection of open intervals, if we choose a single interval, say x comma y, and if the length of that interval is less than delta, then this implies the mod of f of x minus f of y is less than epsilon, and which is actually the definition of uniform continuity of f. So that means we can say that every absolutely continuous function is actually uniform continuous, because by choosing single interval instead of, because it is true for every finite disjoint collection of open intervals, so we can choose single interval also, and by choosing single interval here we get the uniform continuity of f. So that's the next exercise. That's an exercise. Every absolutely continuous function is uniform continuous. Okay, every absolutely continuous function is uniform continuous is uniform continuous is uniform continuous. Show that. Okay, it's an exercise. Show that every absolutely continuous function is uniform continuous. Solution. Let f from closed interval ab to r be absolutely continuous. Be absolutely continuous. We show that f is uniform continuous. F is uniform continuous. So for this we need to show that for each epsilon positive there is a delta positive, such that for any 2 points x and y in the interval AB, mod of x minus y less than delta implies mod of fx minus fy less than epsilon. So let epsilon be any positive. Let we have to find delta. Then by definition of uniform absolutely continuous, then there exists a delta positive such that for any open interval xy in AB, or we can say or we can say for any 2 points x comma y, okay, x comma y in open interval a b with x less than y, either x less than y or greater than y, so we assume this x is less than y. So such that for any open interval x comma y in AB, or we can say for any 2 points x comma y in the interval AB with x less than y, if x minus y is less than delta, then it implies mod of f of x minus f of y is less than epsilon. So this implies f is uniform continuous. F is uniformly continuous function. F is uniformly continuous on AB, on closed interval AB. So that proves that every absolutely continuous function is uniformly continuous. Okay. So next exercise in which we show that every Lipschitz function is absolutely continuous. Exercise: show that every Lipschitz function is absolutely continuous. Every Lipschitz function on closed interval on AB is absolutely continuous. Solution. So let's take any Lipschitz function. Let f from closed interval AB to R be Lipschitz. Then we can find a constant C That's called the Lipschitz constant. Then and let's see be a positive number, which is called the Lipschitz constant. Actually, Lipschitz constant. Okay, let's see be the Lipschitz constant such that mod of f of u minus f of v is less than, or you can say less or equal to c times mod of u minus v for all u comma v belongs to the interval a b. So this is the definition of Lipschitz function actually. Now we show that f is absolutely continuous. Now we show that f is absolutely continuous. F is absolutely continuous. So for this we need to show that for each epsilon positive there is a delta positive, such that for any collection let epsilon be any positive number. Let epsilon be any positive number. Let's take epsilon be any positive number. Then this delta, your delta is actually equal to epsilon by c. And let's take and let this ak bk 1 less or equal to k less or equal to n be any finite disjoint collection of open intervals in AB. Okay, open interval is in AB. Now we have now this summation k runs from 1 to n mod of f of bk minus f of ak. Let's try to find this sum. This sum is less or equal to, because this is Lipschitz function, so f of bk minus ck, mod of f of bk minus ck is less or equal to c times mod of bk minus ak. Okay, and this is equal to summation k runs from 1 to n, it's c times this is just bk minus ak, because bk is greater than ak, and this one is less than epsilon. This is less than epsilon whenever summation k runs from 1 to n, bk minus ak is less than epsilon by c. That's called a delta. So this variation is less than epsilon whenever the sum of the lengths of these intervals is less than delta, where delta is equal to epsilon by c. Obviously this delta depends on the epsilon. So thus for each epsilon positive,